Today we are walking through the paper titled OCR-Memory Optical Context Retrieval for Long Horizon Agent Memory.
What problem is this paper trying to solve?
It focuses on long horizon agents. These agents collect long histories of user turns, reasoning traces, tool calls, and tool results, but their prompt window is still limited.
So the issue is not just remembering more, but remembering exact details.
Exactly. The paper argues that existing memory systems usually choose between two bad options: keep verbatim trajectories and spend too many tokens, or compress them into text summaries and risk losing the evidence needed later.
What is the proposed alternative?
OCR-Memory stores the agent's historical trajectories as images instead of ordinary text. The idea is to use visual tokens as a dense carrier for long logs, then retrieve only the relevant text segments when a new query arrives.
Before the diagram, what does optical retrieval mean here?
It means the memory module looks at images of past interaction logs, not just text embeddings. It uses visual markers to decide which regions matter. Then it recovers the exact associated text from a deterministic log. Now the method diagram shows the full flow. On the left, long histories are stored as compressed materials Airtion images. In the middle, visual anchors mark candidate segments. On the right, selected indices are used to fetch the original text.
Why predict indices instead of asking the model to rewrite the remembered text?
That is the locate and transcribe design. The model only decides which marked segments are relevant. The system then transcribes by fetching the stored verbatim text, so retrieval is less exposed to hallucinated wording.
Where does the formal retrieval step fit into that story?
The retrieval module is written as E equals G theta of Q and M. E is the evidence returned to the agent, Q is the new query. The equation separates retrieval from answering.
Why is it important that retrieval is separate from answering?
Because the optical memory model is optimized to find supporting evidence, not to solve the task itself. The downstream agent still reasons with the query and the retrieved evidence, but it receives far fewer prompt tokens.
How does the system keep very old memories without spending high visual token cost forever?
It uses multi-resolution memory. Recent or important items can stay high resolution, while older history can be stored as lower resolution thumbnails. If a compressed item looks relevant, Active Recall restores it to the original fidelity.
How is the retriever trained to choose the right mark segments?
The paper adapts DeepSeek OCR. It freezes the vision encoder to preserve optical recognition, fine-tunes the language decoder with lower A, and repurposes Hotbot QA so the target is a binary vector of supporting paragraphs rather than a generated answer.
What benchmarks do they use to test whether this helps agents?
They test on Mind2Web for web navigation and AppWorld for API interaction. Mind2Web checks element accuracy, action quality, step success, and task success. AppWorld emphasizes success rates, especially on hard tasks that require backtracking through long history.
What are the main result numbers?
Against the strong AWM baseline on Mind2Web, OCR-Memory raises element accuracy from 49.1% to 53.8%, raises step success to 46.1%, and reaches 4.8% task success. On AppWorld, it reaches the highest average success rate, 58.1%.
Where is the advantage clearest on AppWorld?
On the hard AppWorld split, OCR-Memory reaches 30.8% success. That is higher than standard text retrieval at 21.4% and higher than AWM at 27.2%, which supports the claim that exact long history evidence matters most on difficult tasks. The result plot then looks at strict context budgets from 1024 to 8190 to tokens. OCR-Memory stays ahead of text retrieval across the Mind2Web metrics, and the gap becomes more important when the token limit is tight.
Why does the gap widen when the context budget is smaller?
Text retrieval has to squeeze history back into text tokens, so it loses more information under a small budget. OCR-Memory moves the long history into visual memory and injects only selected evidence, so it preserves useful details with much less prompt overhead.
Do the ablations show which design choices matter?
Yes. Removing set of mark prompting hurts both accuracy and speed. The full model gets 53.8% element accuracy and 46.1% step success with 1.7 seconds latency. The text generation variant drops to 46.5% element accuracy, 39.2% step success, and 5.3 seconds latency.
What about the materialization part?
Static low resolution uses only 65 visual tokens per history frame, but step success falls to 39.7%. Static high resolution reaches 46.5% step success, but uses 256 tokens. The dynamic strategy gets 46.1% step success with 82 tokens, close to high resolution quality with much lower cost.
Does the paper check whether the retrieved evidence is faithful?
It does. On an experience retrieval subset from mind to web, OCR-Memory improves recall at 1 from 50 to 0.7% for dense text AG to 78.6%. For content level faithfulness, the generative retrieval variant gets 84.3%, while OCR-Memory gets 100% because it fetches exact stored text after choosing indices.
What trade-offs should viewers remember?
OCR-Memory is not free. In the efficiency profile, text tokens per step drop from 3,980 to 596, a 6.7 times reduction. But disk usage rises from 18 kilobytes to 1.47 megabytes per episode, and retrieval latency rises from 0.3 seconds to 1.7 seconds.
So what is the final takeaway?
The takeaway is that visual memory can be a practical way to preserve long agent histories. OCR-Memory improves task performance under tight context limits by storing history optically, selecting marked evidence, and recovering exact text instead of asking a model to regenerate it. That wraps up this paper walkthrough.